Reflection and refraction of waves. We're going to focus mostly on light, but these phenomena apply to all waves. Reflection is the bouncing of a wave. And by the way, as I get going here, sorry about the formatting here. The notes are formatted nicely. For some reason on the iPad, the notes got reformatted, and I'll try to deal with that here, but I think you'll get the idea on your note page. But reflection is the bouncing of a wave. The law of reflection is that the angle of incidence equals the angle of reflection. All angles are to be measured with respect to the normal line. The normal. That's a line that's perpendicular to the surface of reflection. Key word there being perpendicular. So for example, in this ray model of light, on the left-hand side here, we have the angle of incidence indicated here in green. Sometimes, and this dashed line right here is what we call the normal. Very important that you draw that every time you do these diagrams and as you calculate these angles in the labs and so forth. So I usually make the normal line a dashed line. It's normal to the reflecting surface, and a reflecting surface doesn't have to be a mirror, but in this case it is a mirror. But we have a light ray, or any wave for that matter, as a ray coming in, angle of incidence here on the left. It's measured with the normal, not with the surface. So we don't want to measure the angle with respect to the surface, but a lot of times what I'll do is I'll call that theta 1. Some books will call that theta I for theta incident. And then you have the angle of reflection. I'm going to call that theta 2. Once again, some books call that, and you can call it theta r if you would like to, but the law of reflection simply states that theta 1 will equal theta 2. Or theta I equals theta r. Now the wavefront model is on the right here. This should go up in this spot. But it shows you the same thing. We usually don't draw the wavefront model when we're applying this law, but you can. You can see how the diagram shows you the blue incident waves, the wavefronts hitting a barrier and reflecting. The blue waves are the reflected ones, and the rays show you which direction they're going. We typically won't be drawing that diagram, but once again, you could draw the normal line, and I usually just draw a dashed line that would come straight down, perpendicular to the surface. So, and that would be the normal line there, this dashed line that I have. We normally won't be working with that diagram. Alright, a little bit more advanced is the law of refraction. Let's define refraction first. It's responsible for, like this diagram you see here with the quote-unquote broken pencil, or things that look like they're bent when they're in water or in a new medium or a different medium. But refraction is the bending of a wave. Once again, we're going to focus on light waves as it enters new mediums. The bending is caused by the different speeds in the different mediums, and I'll give you some examples in class. But the basic diagram to represent this is a little bit lower here, and once again the formatting is a little off. But as you see, you will have an interface surface here. There's air and water, and this black line, horizontal line, represents the interface between the air and the water, and the dashed black line is the normal. Once again, very important to draw the normal. And you have your incident ray here in this diagram indicated in blue. Once again, a lot of times I'll call this theta 1. And then the refracted angle, I'm going to call that theta 2. Noticing that once again these angles are all measured with respect to the normal, not with respect to the refracting or reflecting surface. It's always very important, and you'll be pulling out protractors here in the lab to measure those angles from the rays to the normal lines. The index of refraction obviously has to do something with refraction. It's a ratio. It's defined as the ratio of the speed of light in a vacuum, which is always considered to be 3.00 times 10 to the 8th meters per second. Anyways, the index of refraction, which we indicate with the letter n, index of refraction, is the ratio of that speed over the speed in the medium. In other words, n equals c over v. Mathematically, symbolically, this is the equation. C is in meters per second, and V is in meters per second, so N has no units. N has no units because it's a ratio. So let me give you some examples. So example number 1, what is the speed of light in water? If we simply look at the definition of index of refraction, N equals C over V, if you look at the previous table on the previous page, it tells you, I believe, that the index of refraction of water is 1.33. You find that from the table. I don't expect you to memorize that. Equals C, which is 3.00 times 10 to the 8th, which I will expect you to memorize. You may have it memorized already, over V. So you plug it into your calculator, you get 2.26 times 10 to the 8th meters per second for the speed of light in water. Another example is, in what material would the speed of light be? 1.95 times 10 to the 8th meters per second. Once again, simply N equals C over V. It's fairly straightforward. Now we're looking for N. C, once again, is 3.00 times 10 to the 8th meters per second, divided by your 1.95 times 10 to the 8th meters per second. And the shortcut would be just to take the 3 divided by 1.95. And you end up with N equals 1.54. Once again, that's a unitless number. It's a ratio. And look at now you have to look up the table. I don't expect you to memorize it. Go back and look at that table. And from the table, that matches up with ruby. So that material is probably ruby. Example number 3. You have some light that's in diamond. Now, diamond is one of the most optically dense materials there is. It really slows down the speed of light by more than 50%. You can look it up in the table on the previous page, and the index of refraction of diamond is 2.42. Now I know I'm going to need to figure out the speed of light in diamond. I'm going to do that first in this problem. N equals C over V. That's our index of refraction equation. So we have 2.42 equals 3.0 times 10 to the 8th, standard speed of light in a vacuum, over the speed in the diamond. And it turns out that the velocity of light in diamond comes out to be 1.24 times 10 to the 8th meters per second. That's an important number. That's not the answer. But that's less than 50% of its normal speed. All right. Now we're going to apply the equation that we've been using for quite some time in this unit. It's V equals lambda F. The velocity of light in this diamond is 1.24 times 10 to the 8th equals the wavelength in this diamond, which is 224 nanometers. That's 224 times 10 to the negative 9th, because nano is negative 9. That's not 2.24, it's 224 times the frequency in this diamond. So we can calculate the frequency of this light in the diamond. And it comes out to be 5.54 times 10 to the 14 hertz. Once again, it's not the answer, but it's an important number that's in a diamond. But here's something of note, and that is the frequency stays constant. The wavelength changes as light transfers from one medium to another. The speed changes, the wavelength changes, but the frequency stays constant. Frequency stays constant. It says frequency is constant. Very important to apply that here, because now once you go back into the air, so all of this on the left over here so far has been in that diamond, but if I go back to air, in the air, once again in air we still have V equals lambda F. But the velocity of light in air, we already know, we assume it's just like diamond. If you go back to that previous table, the index of refraction of air is 1.0003 to 5 sig figs. Well, we're not going to get that precise. For all practical purposes, the velocity of light in air is the same as it is in a vacuum. The 2 sig figs or 3 sig figs, that is true. 3.00 times 10 to the 8th meters per second equals the wavelength in air times the frequency, which is the same as it is always. It never changes. The 5.54, sorry, I'm going to squeeze this in here, times 10 to the 14th. That says 5.54 times 10 to the 14th hertz. Same as it is in the diamond. But the wavelength in air is different than it is in the diamond. The diamond makes the wavelength kind of scrunch up because it slows down in a sense. It turns out that the wavelength of this light in air is 542 times 10 to the negative 9th, but that's nanometers. It's customary to put wavelengths for visible light in the nanometer notation. So that's not standard scientific notation. That would be 5.42 times 10 to the negative 7th meters, 542 times 10 to the negative 9th meters, nanometers. That's our answer. Now that would be done. You can also look up and see what actual color of light that is. In air, if you were to view this light, it turns out to be green. That's green light. You didn't need to do that. I looked that up. Every color of light, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, you can look this up in a table to figure out what color that matches. I'm not going to make you do that. If I wanted you to do that, I would give you the table. But you can look that up. You can Google that to see what wavelength of light 542 nanometers is. It turns out that green is anywhere from about 470 nanometers. Once again, I just looked that up to about 550 nanometers. Anything in that range, sorry, it's 470 nanometers to 550 nanometers. Anything in that range is green light. All right, now, Snell's law of refraction. I'm kind of infringing on the space here, but let me use red for this. It looks like this. N sub 1 sine theta sub 1, that's for our initial medium and the angle of incidence, which I'll show you some diagrams of here in a second, equals N sub 2 sine theta sub 2. That's Snell's law of refraction. It mathematically helps you determine the angles at which light will bend as it enters a new medium, where N1 is the index of refraction of the initial medium, N sub 2 is the index of refraction for the second. Oh, I have a mistake here in the notes. This should say, I'll fix that on your copy, I think, of the second medium, of the entered medium. I'll just put second, or the new medium. All right, so theta 1 is the angle of incidence and theta 2 is the angle of refraction. I'll give you some examples here. So as I go along here, I will illustrate this with diagrams, but when light goes into a dense medium, it bends toward the normal. When it leaves a dense medium, it bends away from the normal. It's just the opposite, so you just need to memorize one. I'm actually going to start with diagram or practice problem B here. So the dashed line is the normal, and what we have here is this horizontal black line. And usually we have horizontal surfaces, but we don't have to have horizontal surfaces. Tomorrow I'll give you examples with vertical surfaces like glass and a window and so forth. But you have light traveling in water. Water is the first medium here, so N sub 1 is the 1.33. And it's heading into diamond. So this lower surface down here is diamond with an index of refraction of 2.42. So what happens here is this ray of light is coming in at an angle. They don't give you the angle here. Let me make up an angle here of, say, 55 degrees. It's very important that you use that angle and not the angle with the surface, which would be, what, in this case, 35 degrees. So the 35-degree angle is not that important. I'm just showing you that they're complementary because 55 plus 35 is 90. Sometimes they give you the 35-degree angle, then you simply subtract from 90 to get the 55, because the 55 is the important angle. That is the angle of incidence, the incoming angle before it hits the surface and bends. So right here at this point, the light's going to bend. And it's an abrupt bend. Light's always traveling in a straight line, but when it hits that spot here that I've highlighted in blue, maybe I'll make it red now. All right, the light now bends and travels in a straight line once it's inside. But when you're going to something dense, and diamond is dense because 2.42 is greater than the 1.33. So our n sub 2 is 2.42. The ray of light is going to look something like this. Instead of going straight, it's bent towards the normal. In other words, at this angle right here is less than 55. I'm going to call that theta sub 2 because I don't know what that is yet. And I want to calculate that angle using Snell's law. So that red ray is bent closer to the normal. It's not, the blue ray extended straight on would not be the situation because the light bends towards the normal. So we're going to apply Snell's law here for practice problem B. So I'm simply going to plug into this equation up here, n sub 1, which is water in this case, 1.33, sine theta sub 1, which is the 55 degrees, equals n sub 2, which is the diamond, 2.42, times the sine of theta sub 2. And the only unknown here is theta sub 2. So I'm going to go to my calculator and simply calculate theta sub 2, because that's what the question would be here. What is the angle of refraction here? And theta 2 comes out to be 27 degrees to 2 sig figs, which is smaller than theta sub 1 because it has bent toward the normal. All right, practice problem A, doing this backwards, is a situation where if you look at it carefully, we're in crown glass, the incident ray is in crown glass, and let's say that this angle right here is 47 degrees. Once again, I just want to emphasize that we don't want to use the 47 degrees. We want to use the angle with respect to the normal. If you subtract from 90, that's 43 degrees. That's the angle that we need to use there because 90 minus 47 is 43. That's the angle of incidence for our incoming ray. I'll highlight that in blue. All right, that ray then bends. Instead of going straight, all right, if I go straight, well, I don't want to go straight. I'm imagining a line going straight following the blue, but it doesn't. What happens is the ray bends this way. It looks a little awkward because this angle right here now is greater than 43. The blue ray didn't go straight. The incident ray doesn't go straight. It bends away from that normal, kind of towards the interface, the horizontal glass-water interface. Anyways, that now is theta sub 2. And that would be the diagram. And I will be asking you to draw these diagrams. So once again, we'll apply Snell's law. N1, which is 1.52, sine theta sub 1, which is 43 degrees, equals n sub 2, 1.33 sine theta sub 2. All right. So if I go to my calculator, theta sub 2 turns out to be 51 degrees. So the angle from the normal is bigger than it was on incident. The angle of refraction, theta sub 2, is 51 degrees. And Snell's law tells you at what angle light will be refracted when it enters a new medium.